Good morning.
Good morning, sir.
Good morning, sir.
Okay, so today we'll start a new topic, which is called and this is lecture number 11, right? Kinematic analysis. Okay, so to analyze mechanisms and machines, we have started with, let me start recording. We have started with the number synthesis, where we discussed about the range of movement, mobility, and degree of freedom of a mechanism. And then we have learned the number of links in a mechanism. This is our lecture number 11. Okay, and then in the next part we discuss this dimensional synthesis problems. Am I audible to you?
Yes, sir.
Yes, sir. So the dimensional synthesis problem, we discussed what should be the length dimensions of links. So that fulfills the purpose of the mechanism. Purpose means purpose in terms of position and in a particular guided motion. To fulfill that purpose, we have number synthesis and dimensional synthesis we discussed. Now we will discuss the kinematic analysis, which you have done in your last semester, but I will repeat a little bit because the analytical methods I want to teach you. So using those analytical methods, you can analyze the mechanisms, and a systematic way to do this, and something which we are going to study today is very relevant to dynamics. Okay, because if we have very good idea of kinematics, then we can use those ideas in dynamic analysis. Give me 1 or 2 minutes to figure it out. I have to check my notes. So today we are going to discuss the topic like derivative of a vector, how to differentiate with respect to time a vector. That is one of our concerns. And next is we'll discuss once you learn how to differentiate a vector with respect to time. If the vector is a position vector, differentiating it, you will get the velocity, and if you have the velocity vector. From that, you will get the differentiating it, you will get the acceleration. Velocity and acceleration are the kinematic quantities. We are much interested in it. Okay. So let us start that. You have already learned for a mechanism how to find out velocity and acceleration of a link or a particular point on a link, and you have learned how to find out them graphically. Here we will learn how to find out them analytically. Once you learn the analytical methods for a very complicated mechanism, you can write down those equations and write down computer programs to find out the kinematic quantities with respect to time. Okay. So to start with, let us discuss what do you let us discuss finite rotation. Okay. Finite rotations are vectors or scalars? Rotations are vectors or scalars?
Vector.
Vector.
Why?
Because
It's having
clockwise and
direction also.
anti-clockwise represents.
Huh?
Because
Sir,
of
very
that,
small
direction is
rotations are very small rotations are vectors and bigger rotations are scalars.
Yes, all of you agree with this? Many of you may not be aware of this fact that infinitesimal rotations are vectors, but finite rotations are not vectors. How? Let us see. For example, suppose you take this book. Okay, this is a book. Let us give two rotations. Okay, rotation 1 and rotation 2. And let me ask you the question. So we start with this finite rotations are not vectors. First, we will check this fact. Finite rotations are not vectors. So if there is a vector A and there is another vector B, I am putting this under bar to show this is a vector A. And if you add this with a vector B, then you get this. You can write down B plus A. That gives you the same result. Okay. Now let us take an example to start with this. The two axes I take and give rotation about these two axes. Okay. I'm showing you with the help of this book. So you just take this book and we will give two rotations. One is uh, here. Here I have drawn. One is about the one axis perpendicular to this, another axis along this direction. So let us first give a 90-degree rotation about this direction, perpendicular to the vertical plane. 90-degree rotation, and we give positive rotation. So positive means right hand screw rule, it follows. So I gave a 90-degree rotation. The book, I started from this position and then the book become this position. Now if you rotate about the other axis, so first rotation we have given, this is vector A. If you say that this is a vector, then this is vector A, and then you give another rotation about this axis. So if you give that rotation, you have This is the position. In this position, you see the whatever writing, the front side of the book is just downward. Okay. Okay. So that is the final position. Let me repeat it. From this position, we have given first this rotation, and then we have given this rotation. Two rotations, two 90-degree rotations about, let's say this is x-axis and this is y-axis. About x-axis and y-axis, I have given two rotations. Okay, and I come to this position. All right. Now let's change the order of these rotations. I start from this position, but first let me give this rotation with respect to y-axis. If I rotate right hand screw rule, if I rotate, I come to this position. After first rotation, I come to this position, and then you rotate about the x-axis, right hand screw rule. So finally, you come to this position. Okay. Now, can you see the results? In the first case, we have started from this position, then we have given this rotation, then this rotation. Okay. The two rotations gives us this result. But in the other case, you start from here, okay, rotate it first, this rotation, and then you give this rotation. You have this position. So these two positions are not same, right? Are they same? These two positions are
No,
not
sir.
same.
Both are different.
That means if you call this rotation, each rotation is a vector, then a plus b must be equals to b plus a, which is not true for this case. Do you see it?
Yes,
Yes,
sir.
sir.
That
Yes,
means
sir.
that proves that the finite rotations are not vectors. On the other hand, if you can do a simple experiment with very small rotation, I take this. This is a pen. Okay, I take this pen, and all of you can do this experiment. If you do, then you will understand. So first, again, let us give the rotations about the same axis, but this time we will give very small rotation. So first we will give rotation about x-axis. Okay, so if you give x-axis, it is vertical. Now it will be tilted little bit like this. So I have tilted like this, very small rotation, and then you rotate it about y-axis, very small rotation. You are at this position. Okay, now you change the order of rotation. You first give rotation with respect to y-axis, and then you give rotation with respect to x-axis. You will see that you are reaching to the same position by these two different order of rotation. Okay, have you done the experiment? Can you do it right now?
Yes.
Yes.
Are you convinced?
Yes, sir.
Okay, so let me tell you one thing, that this is the rotation you have given. First we started from this, and then this rotation, then this rotation. And another case, you started from this, then first give this rotation, then this rotation. You reach to the same position. These two positions, result positions, depends on the how much rotation you have given. If your rotation is small, but still not infinitely small, so that gives you a approximately same result. Okay, mathematically we can prove this, but that is not in the scope of this course, so we'll not discuss that. But we can also mathematically prove that if you take very small rotation, infinitesimal rotation, then these rotations gives you this result, a plus b equals to b plus a, which proves that the finite rotations are vectors. Okay. infinitesimal rotations are vectors. Infinitesimal rotations are vectors. Why we are discussing so? Because in rotation, a very important quantity is angular velocity. We need to understand what is angular velocity. The angular velocity is a rate of change of orientation. The definition is rate of change of remember that due to some reason the lander of our lunar this ISRO's lunar project, the lander could not land in the surface of moon, and this is a specific problem of this course only. Again, I am saying this problem is related to you only. You guys can solve. There are few things which are not taken care properly that belong to this subject, dynamics and control. Okay, and whatever we are discussing here is the building block of that subject. Unfortunately, throughout your BTech courses, these subjects are neglected somehow. Okay, but as I said, this is a whole area of research, this is a whole area of working. You can develop mechanisms, automate things, a large scope of working, large scope of product development, creative work, and this is the building block. Okay, so those who are interested, they must pay attention in these small definitions and small things, because sometimes what happen, for your exam purpose you learn something to just to pass or score good marks in the exam. I'm not saying you should not score good marks in the exam. Obviously, that is also a necessary thing. But at the same time, those who are planning for ambitious work and interesting or adventurous work in their life, they must learn it properly. Basic things. Okay, so the rate of change of orientation is called the angular velocity. Generally we designate is with this letter called omega, and angular velocity is actually is a vector which is defined like in delta t tends to 0, what is the change in orientation, and it has a direction. So it has two parts. You see, this is a scalar part. This whole thing is a scalar part, and this gives you the direction. Okay. Now something vector which is this is a vector. Suppose that vector is making a rotation in this direction. Then what is the direction of angular velocity? Can you tell somebody can somebody tell me what is the direction of angular velocity? Suppose initially the vector is here, this one, and finally the vector is here. It is rotating in this direction. It is rotating in this direction. So what is the direction of angular velocity?
Outside the
Plus
paper.
plus Z.
It is perpendicular to this paper, okay? Perpendicular to the board,
Seat and
right?
outside.
And it follows the right hand screw rule, and this cap we are using, you know, the cap we use for unit vector. This is a unit vector, right? Okay. And now we'll move to the next thing, that is derivative of a vector. We want to find out, we are interested in velocity and acceleration. To find out velocity and acceleration, if position, you know that position is a vector, suppose A is a, or R is a vector, suppose R is a position vector, then the velocity, which is also a vector, is the derivative of this R vector. And acceleration, which is also a vector, B is this. Acceleration is a vector which is derivative of V vector. Now, do you know how to take derivative of a vector? How to find out derivative of a vector? You have already done this, but I don't know that whether you have systematically done this or not. So we are trying to develop here the systematic way to develop systematic way to get the or differentiate a vector. Okay. For this, let us first take a vector. This is a vector R. R is a vector. We are taking this as a case 1 where R is a vector whose R is a vector which is not rotating. R is a vector which is not rotating. Its magnitude can change. Magnitude is changing with time. That means if we take, this is the position vector R, at the beginning it is here, and after some time, suppose the R vector after some time is now here. So this whole thing from this point to this point. So with this delta time, very small time, it has this much increment vector. The magnitude is increased. As I said, the vector is not rotating vector. If vector is not rotating, that means it is only changing its magnitude. So this is delta. This change in magnitude, we'll call it delta R. Okay, this change in magnitude is delta R. And we define a unit vector along this direction. Unit vector along this direction. Let us call it E1. Unit vector along this direction. Now, if you want to find out what is the derivative of this vector, what is the derivative of this vector? So the derivative, you can have this definition that limit delta t tends to 0, whatever change in delta t time in this vector divided by delta t. That gives you the derivative. This is the definition from the first principle, derivative definition. And now one thing you see that this delta r can be written as, here I am writing delta r is a vector, okay? Rate of change of r. This is a vector. And this change from here, can you see this change is happening in which direction?
E.
in the E direction. So can we write like this? Magnitude of R and the direction is E1.
Yes, sir.
Okay.
Yes, sir.
So here we can write this is limit delta t tends to 0, and this is magnitude of R, and this is delta t, and the direction is E1. Now you see this whole thing is a scalar quantity, is it not?
Yes, sir.
Yes, sir.
If it is a scalar quantity, we simply write this. This is the differentiation of the magnitude of R. Sorry, this is the differentiation of the magnitude of R. Okay. Some vector which is not rotating, changing its magnitude, the differentiation, when you take the differentiation is the change in magnitude, rate of change in magnitude, and it is in the direction E. Now we take case 2. This is very simple. This differentiation is very simple. Now we take a case where R is a rotating vector, but the magnitude of R is constant. Now what will happen if we want to take the derivative? Let us first draw this, and then we will find out the derivative of this vector R. So again, we draw a vector R here. This is vector R. And as we said that this vector is a rotating vector. Suppose after a very small time, it has rotated to a position like this. Okay. Remember that it is not changing its magnitude. It has rotated to this position. Okay. And this angle of rotation is, let's say, very small angle, delta theta. Okay. And initially the vector is vector R, and finally suppose this vector is R dash. Okay. Now what is the change in this vector? This much is the change in vector. Agreed? Hello?
Yes, sir.
So this is delta R in this case. Okay. As we did for the previous case, we define a unit vector along this direction, and that unit vector is E1. We define another unit vector in this direction, that is E2. And we have unit vector n, which is perpendicular to E1 and E2. And the relation is, when you do this E1 cross E2, you get n. Okay? Is it fine? Are you fine with this? We are defining
Yes, sir.
these unit vectors. And we want to now find out what is the derivative of this vector when it is a rotating vector, but it is not changing its magnitude. All right. And we have taken a planar motion. Just to make it simple, I have just taken a planar motion. Okay, in one plane only, it is rotating. All right, now let us do this derivative. So, derivative of R vector. We are interested in the derivative of R vector. So, you just write down the definition of this derivative. Delta t tends to 0. What is the change? what is what is the change in this vector? That is delta r divided by time. Okay, and now as we did for this case, we will first convert this into a scalar, then only this derivative is very simple for us. So delta t tends to 0, and we write here the magnitude of r, okay, magnitude of r divided by delta t, and now tell me in which direction this change is, in which direction delta r change, in which direction? It is in E2 direction.
E2.
Okay. Just one can argue, how can you say that this is in E2 direction? You consider a very small theta. Theta is very small, infinitesimally small. So the change is obviously along the perpendicular direction of E1, and we are calling it E2 direction. Okay. Fine. So in the next step, what we will do, limit delta t tends to 0, and this is delta r by delta t. Now can we write down this E2 here? From here you see we have written n, the unit vector n, like this. Similarly, can we write down E2 as cross multiplication of two other vectors, unit vectors? What should we write if we want to write down this way? Unit vectors are E1, E2,
N
and
cross E2.
n.
N cross E1.
So we should write n cross E1. So that's what, let us use this here. We are writing here this n cross E1. Okay. When you have this, now if I write down this way, delta t tends to 0. Okay. And this magnitude, can we write it in terms of theta and r? Can we write it in terms of theta and r?
So R delta theta.
This is magnitude of r into delta theta. We can write it this way. So let us put it that way. This is the magnitude r multiplied with delta theta divided by delta t, and that is multiplied with, now you see these quantities. These quantities are scalar quantities, so you can take them any side of this multiplication, cross multiplication. So what we will do now is, let us write it this way. Delta t tends to 0, delta theta by delta t, n cross r E1. Can I write like this? This is a scalar quantity. So you can take any side of this cross product. I have taken it that side. Is it fine?
Yes, sir.
Now, can you see what is this? What is this quantity from the previous definitions?
Omega.
This is omega.
Omega.
So this is omega cross RE1 What is this R, magnitude of R E1?
Vector R.
This is just vector R. So we arrive the result that the derivative of this vector is omega cross R. Now, if you combine these two cases, case 1 and case 2, if you combine these two cases, case 1, we have taken a vector R, which is changing its magnitude, but it is not rotating. Its derivative is given by this. And in case 2, we have taken one rotating vector. Its magnitude is not changing. Then the derivative is given by this. If you combine them, that means vector R is a general vector. It is rotating and changing its magnitude. Then the derivative, it is not very difficult to show, but we are not showing here. The derivative of this vector can be written as this plus this. Okay. ddt of derivative of the magnitude in the direction, other than writing it E1, we are writing it in the direction of R. ठीक है?
Yes, sir.
So here we establish the derivative of any vector. R is any vector. For this case, we said that this is a position vector, but R is any vector. Its derivative can be written like this. Now, if you just say what is this derivative we obtain from one assumption that the motion is a planar motion, but the same formula of derivative is applicable for a space three-dimensional motion. And it is not very difficult to show or prove that, but I leave you with that three-dimensional proof, and that can be done using, you first take a vector which is here, and that vector is changed to this position. The procedure is same. You can follow and you can get this proof. Okay. We are not going to that proof, but for planar motion, this is sufficient. And this same thing is valid for space motion also. Okay, now we will take a general motion. General motion. So general, any particle or any object which is moving, its motion can be represented like this. Suppose there is a vector R. This vector R is a not rotating vector. We call it R0. R0 is a not rotating vector. And we have another vector which is small r. This is small r, This small r is a vector which is rotating with angular velocity. It is rotating with angular velocity omega, and it is changing its magnitude. Okay, this not rotating vector also changing its magnitude. It is just not rotating, and the combination of these two vectors represents position of a point. Suppose we call this point is B and this point is A. A is a general point and its position vector R, this is capital R. So A is a general, B is a general point whose position is given by this vector R, which is actually equals to R0 plus R. Do you agree with this vector equation?
Yes, sir.
Yes, sir.
Position, okay. Position of B. Now we want to find out what is the velocity of point B. Okay. Velocity of B. What is this? To find out that, what we need to do, we need to differentiate this. Differentiate with respect to time the position vector. When you do this differentiation, just first let us write down it. Differentiation of the first vector plus differentiation of the second vector. As you know, for differentiation, if two things are in summation, you can apply differentiation separately, and you have, this is the definition, differentiation. Now let us find out first what is this differentiation. Can somebody tell me what should I write? The first term definition, differentiation, R0.
V0.
Omega cross R plus
Remember that R0 is a not rotating vector.
only dr by dt into
So this is d
unit vector of
dt, and this is the differentiation
magnitude
of
of
the
R.
magnitude, and in which direction? In the R0 direction.
R naught.
Okay. Now let us do the second part. Tell me, what should I write?
Omega cross small r plus d
plus d by dt
dt in direction of r, small r.
Okay. All of you agree? Let
Yes,
us
sir.
put some numbers
sir.
here. This is our, let us call it 11.1. Let's call it 11.2. Call it 11.3. Not this one. This one is 11.3. This one is 11.4. Let's call it 11.5. And this is 11.6. Now in 11.6, what is the first quantity? This is the velocity of point B, right? This is velocity of point B. What is this quantity? From the figure, what is
The
this
scalar
quantity?
quantity.
This is velocity of point A. Okay. Now what is this quantity altogether?
Velocity of point B.
velocity of point B with respect to A. ठीक है?
Yes, sir.
This is velocity of point B with respect to A. This whole term gives you the velocity of point B with respect to A. And A point has this velocity. Then when you add this velocity plus this velocity, you get the actual velocity of point B. Okay. Then from here, we define this term velocity of point B with respect to A is equals to omega cross R plus d dt of. All right. Okay. Now we will move to, we have 10 minutes. I hope I can complete the acceleration terms. After doing this, so this is, let me write it here. This is called velocity of point B with respect to A. Velocity of B with respect to A. Okay, now again, we will start from this 11.6 and we will find out what is the acceleration of B. To find out this, we will start with 11.6 and do the second derivative with respect to time. And now when you do that, again, let us write down this way, very simple, keep it simple. ddt of R0 in the R0 direction plus ddt of omega cross R plus ddt of this. ठीक है? Are you fine with this line?
Yes, sir.
Okay. Let us go and complete the differentiation. First term, tell me what should I write? I am writing, you correct me. Okay? This is only changing magnitude and change of magnitude in the R direction. Okay.
Yes.
Yes, sir.
See, one can argue that suppose there is a differentiation. Suppose the derivative of u v. What we do? Product rule du dt v plus u dv dt. है ना? Any product, any differentiation of two functions u and v, the differentiation is like this. Same thing you can apply here also. This is a scalar quantity. This is a vector quantity. Now differentiation of first quantity into second. That's what we have written here. Next thing is first quantity, then differentiation of second quantity. Now if you do the differentiation of this quantity, what you will get?
0.
Zero, na?
Yes, sir.
If you just go back to our definition of derivative of a vector and here you put a unit vector, then first quantity is omega cross that unit vector. What is the unit vector of what is the omega for this unit vector? It is 0. R0 is not a rotating vector. So that means this quantity would give you 0. And what is the derivative of the magnitude of a unit vector? 0. So that is why the second term we have not written. Now we will apply the same product rule for this derivative. So you write here this cross R plus omega cross ddt of R plus, now for this case, first again we will apply the product rule, differentiation the product rule we are applying. So this is the d2 of this magnitude and it is in the R direction. But then this R is no more this R is a rotating vector, is it not? Hello. So we have another term.
sir.
We will get another term here. What is that term? That means the first term d dt, its magnitude derivative. Now we have to take differentiation of this unit vector. What will be the differentiation of this unit vector?
Omega.
Go back to this. Here if you put just other
Omega.
than this unit vector, then which quantity we will have? Omega cross the unit vector.
Yes, sir.
Anna? Omega
Yes, sir.
cross the unit vector, and this quantity will be 0 because derivative of the unit vector's magnitude is 0. Okay.
Yes.
So we will write here omega cross the unit vector. So here we are writing omega cross the unit vector. Let us rearrange. What is the physical interpretation of these quantities? We will discuss. Don't worry. So now in this case, we are calling it omega dot. Okay? Derivative of the angular velocity. We are calling it omega dot. And omega dot cross R plus this quantity is omega cross. Now what should we write for this? Bolo,
R
फटाफट
dot.
बोलो. Eh?
Omega cross R.
Then ddt of magnitude's derivative in the R direction. Agreed? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Be with me. If you have any issue, let me know. We have no hurry. This is very important concept. So I'm just now writing, this is a scalar quantity. I'm writing this omega first in the left hand side, and we are writing this scalar quantity multiplied with this. To make some sense, can I write like this?
Yes, sir.
Be with
Yes, sir.
me for 5 more minutes. I will complete this, and then tomorrow we will discuss the physical significance of each quantity. We'll take several examples to understand its application. Okay, now this is first, this quantity is omega dot cross r plus this quantity is omega cross r plus we have this quantity is omega cross देखो यहाँ this quantity omega cross ddt of this into r, the same quantity is here also, ठीक है ना? So we are just
Yes, sir.
writing 2 into this ddt of r, right, plus what is left is this quantity. This is in r direction. All right, make it. We are almost done. Now let us write down these quantities in terms of some physical term. A for acceleration, okay? Acceleration of point B is equals to acceleration of, what is this? This quantity.
Point A.
Acceleration of point
R.
A. Acceleration of point A. Just look at the picture. Double derivative of this gives you acceleration of point A. Okay. And then we have omega dot, we are writing it alpha. Okay. Alpha is the angular acceleration of this r vector. We'll define it here. One by one quantities. Let us write down here. This is acceleration of point B. D2 R0. Just be with me for 5 minutes. This is, we define acceleration of A. Then this omega dot, we are calling it alpha, which is the angular acceleration of r. Alpha cross r plus this is omega cross r plus this is 2 omega cross, we are calling it v relative. Okay, v relative. Tomorrow I will discuss what do we mean by this v relative, and we will solve some problem graphically and analytically to understand this properly. And the last term is, we are calling it a relative. Okay, all these are vectors. So a relative is defined as d2 dt2 in the r direction. Okay, this formula, which is 11.7, is called 5-term acceleration formula. Okay, this is called 5-term acceleration formula. It's a very important thing. You have studied fluid mechanics. I don't know whether they have done this in the class or not. In fluid mechanics also start with this. Any particle, its acceleration can be presented with this. So any object, its acceleration can be presented by these 5 terms. Okay, 1, 2, 3, 4, 5 terms. Right. Today we don't have time. Tomorrow we will discuss what are the physical significance of all these quantities. We'll take some example to understand this. Okay, up to this, if you have any doubt related to this derivations, you can ask me. Any doubt you have? I'll send you today this lecture note and all the previous lecture notes which I have not posted. I'll post today. Okay, if you have any doubt, ask me right now.
Sir, any other book that we can follow for number synthesis and dimensional synthesis? Except etc.
I have only followed that book only. Okay. Because that is a very standard work, so I follow that book only. Professor Mullik also has written some book on mechanisms. That book is not available in the market right now. I searched for it. Okay, other books like Indian books on this topic, I don't recommend. Not that
Number
book.
given in detail in that book.
Hmm?
Number synthesis is not given in detail in that book.
No, see, the whole thing, number synthesis and dimensional synthesis, this is a huge thing. It is just an introduction. Okay. The beauty of the book is it does not spoon feed you. It gives you scope to think about. Okay. If you don't have any more question, see
सर
you tomorrow. हाँ बोल.
सर ये जो हमने ए वेक्टर बी वेक्टर लिया इसको हमने जनरल मोशन बोला, लेकिन जो हमने केस 3 लिया था उसको जनरल मोशन क्यों नहीं बोला?
So you are saying that the combination of case 1 and case 2. इसको,
Yes sir, it was for the general, right?
why your question is why we have taken this R0, right?
Yes sir.
You can only use this because you will see that when there is some object moving in space, suppose this R, okay, this R is moving in space, then always there should be some acceleration to this end or some velocity to this end. How will you determine that? For that we have taken this. And
The screen share is off.
okay, I'm sorry. Just see this, that suppose just consider a link, okay, coupler. The coupler is moving in space. Coupler rotates, also translates. Okay, both the things are there. Although for a coupler the magnitude is not increasing, but suppose there is a link whose length can increase. Such a system we see when we see the earth movers, है ना, JCB बोलते हैं ना. In those cases, you will see a link is changing its length, right? वो piston से निकल के आते हैं, है ना? Changing its length. That means it is changing its length. Also, it rotates. Okay, so that kind of this R, small r represents that, but that link is attached to something, right? That means to find out velocity and acceleration of the end point, you need to know what is the velocity and acceleration of this tail position of this vector. So throughout this derivative, you see when we find out the velocity, This represents the velocity of point A. Okay, the tail position, velocity of point A. And from this part, you will get the velocity of point B with respect to A. Similar thing happens for the acceleration also. This is the part, this whole part is the relative acceleration. Means the acceleration of point B with respect to A. And this gives you the acceleration of point A. That is the purpose of this R0. Okay?
Sir, to take more general case, shouldn't we add one rotation to A also? Give it an omega, so we have
No.
two rotating links.
No, you just understand this. When you suppose there is another link here which is connected to some other link, you want to say that that is also moving, then that is nothing but this case only. Why should we go for that? All the cases can be
No, sir,
represented
I'm
by
saying that
this. All the
I'm saying
cases,
that A is also rotating and changing its
yes,
magnitude, as well as
yes.
B is also rotating.
Then first we will do analysis of that link. When we do analysis of that link, the same formulation is valid. Do you understand? Do you get my point? This formulation can be applicable for any link where there, you will see tomorrow we will discuss the cases where this R0 is not there. This is 0. Only R is there. Okay. When
Okay,
we will discuss examples, then you will see what is the requirement of this. Okay. And unnecessarily complicacy should not be there. Only the necessary things are there. Okay. Again and again, I am saying this is the building block of a whole dynamics. The missile, the all kinds of missiles, all kinds of dynamic motions, control. Nowadays, they are developing the 5th generation fighter jet. This is the building block. Okay. Thank you. See you tomorrow.
thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.